Hello class. Today we're going to be starting our note packet on impulse and momentum. We're only going to be covering the first page today. So if you've got your implements ready to write with, I've got several colors on here, but you can just do it one color if you want. All right, so the first thing we need to understand about today's lesson is we need to go back and remember a particular term, and that is the term inertia. And if you'll remember from last semester, inertia is an object's resistance to any change in motion. Remember, that's why we said we wear seat belts, so that if we have to slam on the brake of our car, the seat belt transfers the braking force to us via our seat belt so that it overcomes our inertia and keeps us from flying through the windshield. All right, now one way of comparing inertias of various objects is to look at how fast they're moving. And we call the quantity of inertial motion momentum. Momentum is denoted with a lowercase letter p because we already use capital P for power. It is a vector quantity, and specifically it's the product of mass and velocity for that object. Product, if you'll remember, means to multiply. So to find the momentum of an object, you take the mass and multiply by the velocity. The direction of the velocity will be the direction of the momentum. It is measured in one of two ways. Knowing that mass is in kilograms and velocity is in meters per second, you get a product, kilogram times meters divided by seconds, or kilogram meter per second. Kilogram meter per second. Or you can also use Newton seconds. And here's why you can do that. A kilogram meter per second squared is a Newton. So if you multiply that by a second, then you get a kilogram meter per second. So a Newton times a second is a kilogram meter per second. So that's why we can also say Newton seconds. I don't really mind whichever one you use. That's up to you. I prefer Newton seconds because it's quicker. Okay, now let's talk about this formula right here. Let's suppose that we have a car and a semi moving at the same speed, 70 miles an hour, down the interstate or along the interstate. Which one is going to have more momentum? Well, it's fairly obvious that even though they're the same speed, they have different mass. And the semi is going to have much more mass than a car. So the semi, m times 70, will have much more momentum than the smaller mass times 70. On the other hand, what would you have if you had two identical VW bugs? Both have the same mass, but one is traveling at 10 miles per hour, the other at 50 miles per hour. Well, since the mass is the same, but their speeds are different, the one with the larger speed will have the larger momentum, and that would be the one traveling at 50 miles per hour. So, more speed, more momentum, more mass, more momentum. Now look at this example. We have a train that's traveling down the track at 63 meters per second. What is its momentum? So we're going to use the formula, chuck in the mass, chuck in the speed, and we get 346,500 Newton seconds. And the direction of that momentum would be the same as the velocity. We would assume it's the positive direction in this case. Now, just like an object can undergo a change in kinetic energy or a change in potential energy, an object can also undergo a change in momentum. Now, why is that? Well, we don't usually, once we've identified our object, we don't usually change its mass, but we can change how fast it's moving. And if you change how fast it's moving, you change its momentum. So look right here. We can also write change in momentum several different ways. It depends on what you want to do. We can, using delta, say, it's the final momentum minus the initial momentum. And if you substitute appropriate MVs in for that, you could say it this way. Or if you factor the M out because it's the same M for that object, then you get the mass times the quantity change in velocity. Remember, the mass typically doesn't change for a given object, but its velocity can. So you can say mass times change in velocity, which would give you the change in momentum. I like to use this way, it's a little easier. Look at this example right here. You have a train, same train as in the first example, but now it decelerates or slows down to 18 meters per second. So we have a new speed. Therefore, we have a new momentum. Now, look what they ask. What is the change in the train's momentum? So I did this. I set up the change in momentum from right up there. Okay, well, right there it is. And I said, it's the mass times the change in velocity. So I said 5,500 times 18 minus 63. Now notice, final minus initial. And look what we get. We have a decrease in momentum of 247,500 Newton seconds. In other words, the change in momentum was actually opposite the direction of velocity because you're slowing down. On part B, they want to know, is it a loss or gain? It is a decrease or loss because the speed is decreasing, as indicated by the negative sign on the answer. Now, I don't know about you guys, but I know that from our discussion of dynamics in the last few months, we know that if something is slowing down, if it's decelerating, that's because it took a force to do that. And what I want to look at for the next couple of minutes is how that force relates to our change in momentum, because the force is what makes the mass decelerate or change velocity. So there must be a relationship between force and momentum, since momentum also depends on change in velocity. So let's look. Don't forget Newton's second law. If you have a change in velocity, it's because you're accelerating or decelerating, so Newton's second law is going to hold here. Now, impulse. This is where the force comes in. A new quantity called impulse, and we use a capital J for impulse. We don't use a capital I. That's because capital I is already being used for at least two other quantities in physics, and we can't use it for a third. So they use a capital J for impulse. Notice what it is. It's the product of force acting on an object in a time period. So impulse is the product of the force that causes the change in momentum in the time period it acts in. Okay? So, in other words, the bigger the force, the bigger the impulse acting on the object. The longer the force acts, the bigger the impulse on the object. Now, here's what's neat about the impulse right here. It not only causes the change in momentum to occur because it's a force making the velocity change. Not only causes it, but it's also equal to the change in momentum. So, we call this idea the impulse momentum theorem. Okay, let me show you this side first, and then I'll slide it over. The impulse momentum theorem. It says that the impulse J equals the change in momentum. It causes the change in momentum to occur, and it's equal to the change in momentum. Now, that's sort of analogous to what we already learned about work. We said work causes energy to be converted from one form to another, but it's also equal to the amount of converted energy, the change in energy. So it's a very similar situation. Impulse causes the change in momentum to occur, and it's also equivalent to that change in momentum. We could also write it like this. Since impulse is F times T, and change in momentum is m times the change in velocity, we could write it like that. Sometimes that is very helpful. All right, look at this example right here. We have a baseball thrown by the pitcher toward the batter. It says we are given, or he gives the ball an initial velocity, and we take toward the batter to be positive direction, positive 25 meters per second for that ball. The batter hits the baseball with his bat, and the ball goes flying off with a velocity in the opposite direction, negative 48 meters per second. So when the batter hit the ball with his bat, the bat applied a force in a time period on the ball. That's impulse. And yes, it was a very tiny time period, but it was still a time period. So the ball's momentum changed. So let's take a look at it. In order to find the change in momentum of the ball, okay, is that better? In order to find the change in momentum of the ball, we take the mass and multiply by the change in velocity. But now remember, it's always final, and these are vectors. Negative is the direction, final minus the initial in the positive direction. So this one's in the negative direction, this one's in the positive direction, final minus initial, and look what we get. So the change in velocity is not 23, okay? When you just look at the numbers, you think, oh, that's going to be 23. No, it's not. Think about it. The ball is traveling 25 meters per second when it's headed towards the bat. The bat must first slow the ball from 25 meters per second to 0, then accelerate it from 0 to 48 in the other direction. How about that? So we end up with a much bigger, we end up with negative 70, what would that be, negative 73? We'd end up with negative 73 for the change in momentum, change in velocity. So that's a much bigger change in velocity than you think, and it always will be that way if you also change direction. Now, multiply by that by the mass, and we get a change in velocity of negative 36.5 Newton seconds. In other words, the change in momentum was toward the pitcher. Okay. The next question is, what magnitude impulse did the bat give to the ball? All right, well, the impulse is equal to the change in momentum. I don't need a force. I don't need a time period. All I have to do is remember that impulse equals the change in momentum as well as causing it. So if the change in momentum is negative 36.5 Newton seconds, so is the impulse. And this is my proof, since there's no mathematical work to do. We always write down the theorem for our proof. Lastly, if the bat is in contact with the ball for 0.06 seconds, what force was applied? Well, we now know the impulse, and we know the time period the force acted in, so now we can use the definition of impulse, and I've solved it for F by dividing the T over. We can get the force. Notice the direction of the force is negative, and that should make sense. Since toward the batter is positive, then when he swings the bat, it applies a force on the ball in the negative direction, or toward the pitcher. And this is the value of that force. Okay, so you do have an assignment in your folder to practice using momentum, impulse, and the impulse momentum theorem. Okay? Any questions you can submit as messages or in the discussion box for the conference today, and that would be fine. Have a good day.